Topic is based on remote sensing, and remote sensing is a sophisticated technology which permits precision recording instruments to operate from high altitude vantage points. So, the proper definition for remote sensing is the measurement or acquisition of information by a recording device that is not in physical contact with Earth's surface. So, originally utilizing only airplanes, remote sensing was revolutionized by the use of satellites. Now, more than 1,200 Earth observation satellites from dozens of countries are perched high in the atmosphere. Satellites circle the Earth in a low orbit or in a lofty geosynchronous orbit. And geosynchronous orbit means that this allows a satellite to remain over the same spot on Earth at all times. These satellites gather data and produce images that provide communications, global positioning, which was based on our last week's lecture, GNSS. Also, it provides data about weather and a variety of other information for a wide range of commercial and scientific applications. An example of a specific application is based on land use and land cover change. So, this satellite imagery is based on Las Vegas, Nevada, and Las Vegas, Nevada has been one of the most fastest growing cities in the United States, and we can see that here based on the urban development in 1984 to 2011. We could see the urban development has increased, and even more so now if we have a satellite imagery in 2024. So this Las Vegas was viewed by the Landsat 5TM sensor, and Landsat Satellite Archive allows us to keep a constant eye on urban growth within the fragile ecosystems. So this Landsat imagery of Las Vegas in 1984 and 2011 gives a dramatic look at the growth in urban developments, which includes housing, shops, utilities, and tourist locations necessary to accommodate the growing population and visitors. With this monitoring, we can then use GIS to analyze different planning and water management strategies for the city. And we could see here that Las Vegas is nearby Lake Mead, and we can see how Lake Mead has drastically decreased in size from 1984 to 2011. So remote sensing satellites will allow us to monitor these kinds of impacts and growth, whereas GIS will let us analyze the patterns. So next we're going to talk about aerial photographs. So until the 1960s, aerial photography was almost the only form of remote sensing, and this started as photographs from balloons, then it led to a science of photogrammetry. And this is an important source for USGS to have large-scale geographic imagery. So other organizations may have replaced aerial photographs, but USGS, it is vital to keep on using aerial photographs just for the purpose of large-scale geographic imagery. An example of aerial photographs are orthophoto maps. Here is an example of the orthophoto maps. Orthophoto maps are multicolored, distortion-free photographic maps, and these are prepared from aerial photographs or digital images. Distortions caused by camera tilt or difference in terrain elevation are removed, and they show landscapes in greater detail while retaining common scale to measure distances, and it's most useful in flat-lying coastal areas with low relief. So here in this figure 216, it's an orthophoto map of Wilmington, North Carolina. So next, we need to talk about the electromagnetic spectrum. This figure is based on the electromagnetic spectrum. Visible light and infrared sensing are wavelength-specific ranges of the spectrum. So here we see visible light and infrared, near and far. So electromagnetic radiation includes a wide range of wavelengths that we see here of energy emitted by the sun and other objects. So this includes our visible light, infrared, UV, and radio waves. So one of the most important advancements in remote sensing came when wavelengths of radiation other than visible light were first utilized. So do keep in mind that these are the shorter wavelengths which have higher energy compared to the longer wavelengths which has a decreased amount of energy. Color infrared imagery uses electronic sensors or photographic film to detect near infrared wavelengths. So again, when we look at the electromagnetic spectrum, these remote sensing satellite sensors are only sensing the near infrared, this portion of the electromagnetic spectrum, which are longer wavelengths than what our eyes can see. So our human eyes can only see the visible light part of the spectrum, but these remote sensing satellites can capture what we cannot see with our own eyes. The images produced in this way are called false color, and we can see in this image the living vegetation appears red instead of green, and the bare ground, which we see around here, has a bluish gray tint. So this is useful to identify and evaluate vegetation or the different types of vegetation. Thermal infrared sensing. These are thermal infrared wavelengths cannot be sensed with conventional cameras or photographic film. As a result, special supercooled scanners are needed. Thermal scanning measures the radiant temperature of objects and yield photograph-like images. So here's an example of a high-resolution thermal image of a coal-fired power station in United Kingdom. So the photograph-like images produced in this process are particularly useful for showing diurnal temperature differences between land and water, between bedrock and sediment for studying thermal water pollution, and for detecting forest fires. Next, we'll be talking about multispectral remote sensing. Most satellites today are multispectral or multiband instruments. This means that they detect and record many bands of the electromagnetic spectrum at the same time. And this data is conveyed as a matrix of numbers, each representing a value per pixel and band. So this figure below shows you the process of the remote sensing satellite and how it converts its data to a digital image. So if I could zoom in here, let's see. So we can see here that on the first portion that a satellite collects 30-meter resolution images and it stores it as a matrix of digital values. So here we could see the digital values, so 30-meter resolution, and then the 30-meter value. So 30 meter is the spatial resolution and the size of the grid. So the image is stored in satellite as matrix of digital values, and this digital image is based on band 1, but we could see that there are other bands that this satellite has taken simultaneously. So we have band 1, band 2, all the way to band 11. And then these digital values are sent to the satellite received on Earth. This is a satellite receiver. And then next thing you know, this is where the satellite receiver is sending it to the computer, and the computer manipulates and enhances the data, which can be used to create the digital image. So all the digital images that we've seen are produced in this way. Okay, trying to sense it back. So when we're looking at the different types of satellites, one of them is called Landsat, and Landsat originated at NASA, and currently there are 8 orbiting satellites. So in 1999, NASA launched the first of the Earth observing system satellites known as Terra. So here we have Terra and Aqua, which circle the Earth. And the key instrument of these satellites is MODIS, which stands for Moderate Resolution Imaging Spectroradiometer. And this gathers data in 36 spectral bands and provides images covering the entire planet every 1 to 2 days. And this collects the range of data values and produces numerous images. And also we have commercial high-resolution satellites. And these are very high-resolution imagery using small, lower-cost satellites. Here, this is an example of Landsat 8 satellite image of Acadia National Park in Maine. And our next table, we're going to be looking at the bands found in Landsat 8. So here we could see the bands of Landsat 8, band number 1 all the way to 11. It tells you what portion of the electromagnetic spectrum these band numbers are getting. So here, for band 1, we see that it's only covering the range of 0.43 to 0.45 micrometers, which is a specific range in the electromagnetic spectrum that I just went over. And this band name is called the coastal aerosol. And the resolution is 30 by 30 spatial resolution. And it's saying this can be applied, our typical application, to coastal and aerosol studies. And if you want to use vegetation analysis, this is when we says here vegetation analysis, you would want to use the green band 3, and this is covering this part of the electromagnetic spectrum, and it tells you it's applied to vegetation. So when you are working with remote sensing data, it's important to look at the bands of the specific of your specific study area. So if you are if your specialization is vegetation, you would want to choose a satellite that shows vegetation as one of its bands application. So our next one is, this is trying to adjust my screen sharing setting, but it looks like it messed up. But here we can see this is figure 221, and this is the natural color satellite image showing the Aleutian Islands extending to the southwest from the Alaska Peninsula. And this is showing the Katmai National Park, which is located at the northeastern end of the Alaskan Peninsula. And this image was taken with the MODIS instrument aboard NASA's Aqua satellite. Okay. So lastly, we are going to cover active sensors. So we just covered passive system sensors, and passive systems sense natural radiation, and active systems has its own source of electromagnetic radiation. And these are examples of active system sensors. So radar, which is an acronym for radio detection and ranging, senses certain wavelengths, and this penetrates atmospheric moisture. So radar is good to look at regions that have cloud cover. So the tropical wet areas, the tropical rainforest, they constantly have clouds. So you would want to use a radar sensor to penetrate through the clouds to get the vegetation or the forest underneath it. Next, we have sonar, or sound navigation and ranging, which permits underwater imaging. And last, we have LiDAR, which uses reflected laser lights to measure distances, and this offers 3D information about surface features. So here is an example of LiDAR. We see a 3D dimension of our surface features. And this figure is an example of radar. So that's it for this week's lecture. Please let me know if you have any questions. Thank you for watching.